So, question number one, there is no gravity in a vacuum. Now, I'm not talking about the vacuum that, not that kind of vacuum.
Oh, that's what I thought too. Not even joking.
Okay, well, let's start again. In a space kind of vacuum, where there's no air. Now, can you even make that on Earth? Like, can you get all the air out of something?
No.
You can get pretty close, right? Yeah. You can hook up a pump and you can pump out all the air inside an object, right? A box, I guess, sealed off. So, is there gravity?
No.
There is no gravity. That answer is false.
What? Wait, what?
False. There is gravity in a vacuum.
Yeah, I think so.
There is no gravity in a vacuum. You do have to be careful with true-false answers, don't you?
Yeah.
Questions, right? There is no gravity in a vacuum. That is false. If you're writing down something, you would write, there is gravity in a vacuum. Gravity exists everywhere. What about space? Still a little bit. It is what?
It is in space.
It is in space? Like a lot? Well, it does depend, yeah.
Depends on how far into space.
Okay. Well, more on that soon. Real soon. NASA has built a zero gravity chamber, like a room. That is false. NASA has not built.
If they try to,
That I know of.
wouldn't be surprised.
Where do the astronauts train?
In a plane. In a plane that goes.
Oh, that's true. Yeah. Did I show you the video?
Yeah.
Right? So
Have we tried to figure out how much it costs?
They also train in the water.
they train in the pool, yes. Most of the time they train in the pool. They also train in what they call the Vomit Comet. And yes, you can go on it. $5,000, I think it was, right? Is that right, Gary? So there is a zero. The water is not zero gravity, but it sort of simulates what they do. In fact, I'm just reading. Anyone know who Chris Hadfield is? He's a Canadian astronaut. I'm just reading his biography now at home, and he was talking about one time he was in space and they had a problem, and so they were trying to figure out how to solve the problem. They immediately recreated the problem in the pool and had astronauts in the gear, and they were trying to figure out how to do it in sort of zero gravity kind of situation. So they use that pool. It's like right there, and they jump in and they use it. Gravity is the same as air pressure. False. What is air pressure? PSI, pounds per square inch, right? Yeah. So like right now, are you feeling air pressure? Yeah, we're just used to it, right? So yeah, gravity has nothing to do with air pressure.
Yeah, it's like when you fly in the plane, you feel the pressure.
Yeah, that's true. Gravity pushes down.
False.
Why false?
Because it pulls.
Because it pulls. Sorry, I did. I'm a trickster. Aren't you glad it wasn't a clicker and I made your mark go down? They have been seen to be all false so far, aren't they?
Yeah.
Now, is that a strategy that you should use on multiple choice questions?
Yeah. Well, the answer is the answer.
The answer is the answer. Like, no teacher's going to come up with a, oh, I'm going to get them, and I'm going to make a pattern that they'll never guess. True, false, 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 false. No.
It's possible.
It's possible. Take each question individually. Gravity is the same as magnetism. Well, what do you know? It's false.
I knew it.
What's one difference between magnetism and gravity?
Gravity has something revolving around it. Magnetism is just attraction.
Well, magnetism will pull, attract. Did I say magnetism? Yeah, magnetism will attract, and magnetism can also repel or push, right? Can gravity do that?
No,
Can gravity push?
It can only attract.
Can only attract. So that's, yeah, one major difference. Gravity in space is zero. False. 100% false. I have an Earth, a model of the Earth up here, right? And I'm going to use this tennis ball as the moon. Now, this is not the scale. Pardon me? Oh, yeah? This is not the scale, but what? Like, the moon does this, right? The moon revolves around. Oh, wait. Okay, go ahead. Yeah. There we go. The moon revolves around the Earth, right?
Yeah.
What causes that?
Gravity.
Oh, so there's gravity on the moon? Like attracting it to the Earth? Earth's gravity is attracting the moon. Absolutely, Josh. So the space shuttle dudes, they're like, here's the moon. Space shuttle doesn't exist anymore. ISS, International Space Station dudes and dudettes are here. So there's gravity here?
Yep.
But they're closer than the moon.
Yeah. There's just a stronger gravity where they are.
Aren't they kind of, you know,
Doesn't really have its own gravity.
the moon does have its own gravity.
Yeah.
And the sun also has
The
gravity.
sun does the sun, even way out at Pluto, does the sun attract?
Yeah.
That's what's holding Pluto in orbit. There's a lot of gravity in space. The idea that there's no gravity in space is bunk. Okay? And I'll explain more about that whole weightless thing in a little bit. Okay, now,
I messed this one up, I just realized.
do you guys know what a full moon is?
Yeah.
Like when the moon is completely whole,
Yeah.
right? And there's more moons, so there's a higher gravitational pull creating a higher tide.
No.
Yes, yeah, it's true.
That's
Like,
false.
just kidding.
It's true.
Isn't it
I can't answer that.
Okay, you guys clearly don't understand. When the moon is, go ahead, Jared.
I was just gonna kind of explain it. It's a full moon. It's not like that part of the moon's gone. It's still there.
Yeah.
Yes, absolutely. It's still there. Why do you only see a quarter of the moon?
That's
Just
just no
its
light
position.
reflecting
It's
off.
position where the sun is, right? The
Yeah.
Earth is blocking
Part of
That part is
part of that. Okay? So no, it is not higher gravity because it's a full moon. The moon is still there.
It's a full moon because it's closer to the sun.
No, it's a full moon because of its relation.
What about when the moon's really so close?
That's called a supermoon.
And is that when the tides go high?
That is true, yes. And we recently had a supermoon. Now, you often see on Facebook, and this drives me absolutely crazy. Oh, go outside tonight. Supermoon, it'll be like this, and like the moon is like, you know, really? Really, you guys? First of all, don't get your news from Facebook. Second of all, when you do get your news from Facebook, because I have to admit, I probably get a lot of my news from Facebook now too, right? But when something like that sounds kind of fishy, what should you do?
Go outside.
Well, you could look outside. That would be an excellent way to determine whether it's true or not. Like, oh, look at the moon. It's not near as big as this. Identify for yourself, right? But yeah, Google it, right? How close will the moon be? What will it really look like, right? Use your head a little bit here. It's not going to be, I suppose.
And we do it every year.
Oh, yeah, every year, exactly. Right? Or there's someone always a month later, right? No, the full moon is because of, right? Here's the sun way out here. Hold me the sun. Oh, John, be quiet now. You know what I should play? We should play turn in your cell phone ball. Right, throw the ball, and if you don't catch it, you have to turn in your cell phone. Yeah. Okay, Gigs, catch the ball. Oh, turn in your cell phone. Sorry, bad toss. You guys are pretty gullible. Okay, I'll play that, sure. Hold the sun. If the moon's over here, are you going to see any moon? No. Why not? It's like kind of like almost like an eclipse kind of deal, right? Like it all depends on where the sun is. And I, to be honest, I don't really sort of understand it all. Will I understand if I look at it for 30 seconds? Yes. But it's got nothing to do with the size of the moon. The moon is still there. Thank you, Jared. It's a long walk all the way around here. Okay, what's the next one? Oh, I think I know what it is. Oh, yeah, no. Please tell me you all got this one right.
Oh, yeah.
Yeah, of course.
Obviously, it's on the bricks.
Can't
Obviously.
tell.
Did you write down those?
Obviously, see.
Oh, yeah, leave it.
Right? A pound of bricks, a pound of feathers weigh the same. A pound is a pound. It's a weight of force, right? It's a unit of force. Right? You're just gonna have a whole lot more feathers, that's all, right?
A lot of feathers.
A lot of feathers. Okay. Black holes. Now, read the question carefully. One other reason why I do this as well is because you've seen true and false on tests. You're going to see more and more of them, right? I'm not a big fan of true and false. They're terrible questions. But if you're in physics, good chance you're going on to post-secondary. They love true and false, and they love multiple choices. It can be marked by a computer. So I want to give you a little bit of experience with that. So here's sort of some more experience. Black holes don't suck everything into them. Terrible true and false question. Why? Because it has the word don't in it. You should never write a true and false question with the word don't in it. That said, you're going to see them. So let's analyze this. Black holes do not suck everything into them. True. They do not suck everything into them. Jared, are you in a black hole right now?
No.
Well, then they don't suck everything into them, right? Because you would be in there.
They can suck light in though.
They can, but that's not everything.
That's not.
We are clearly not inside a black hole. I'm sorry, I keep getting really close to you here. It's
I thought you meant like
a little awkward.
vicinity of one.
Hey?
I thought you meant like when you were next to them.
That's what you got to understand.
You gotta read the question carefully. Let me explain. Okay, let me explain what a black hole is first of all. First of all, a black hole used to be a star, a sun.
Yeah.
Yeah.
Okay? And I explained this in grade 12 to further depth, but I'll give you sort of the quick version. That star, because of reasons that I won't go into, basically collapses in onto itself like this. Oh, this is good. I've never done this before. Right? But like way more than that. See how big it was before? How come it's big like this? It's got air. It's got air in between, right? Like, you know, like it's sponge, right? And all that empty space gets crushed out. But I'm not near as powerful as gravity, right? Have I squished all the air out? No, there's still plenty of air in here, right? In fact, there's kind of for this. I'm not stealing your wallet, right? Lawson's wallet has space in it, right? As does this calculator. This throws a bottle of water, right? There's space in between the atoms, between the protons and the electrons, right? And so in this black hole, even that space is reduced. And so the density, you guys know what density is, right? The density of the black hole is unimaginable. You can't, we cannot understand how dense it is.
Is this supposed to be like the weight of the star, like in that one point?
Yeah, the entire mass of the star is down to that tiny little point. It is, you can't imagine it. Tiny close.
If you put Mount Everest and switch it down to the size of a sugar cube, you get a black hole.
Even smaller.
Yeah.
Even smaller. Even smaller. Okay, so now, what orbits stars? Planets. So here's the red planet orbiting. Now, usually what happens, stars expand and then they collapse. But so eventually this sun is going to no longer be there. It's all going to be just a little tiny dot. What does the planet do? Right on doing what it was doing before, which is orbiting. In fact, that's how they determine where black holes are. They look for planets that are orbiting nothing. And what's the nothing? Black hole. Okay. Does it still have gravity?
Yeah.
How come? Because it still has the same amount of mass, Josh. Still has the same amount of mass. Now, what will it suck in? Now, if I draw the sun back up there, right? So if you were to fire something at it, and it would then fall to the surface of the sun, guess what? If it's no longer there, I should have drawn that as a different color. Let's try it again. Right? Here's the blue one, right? I shoot something at it and eventually it falls to it, right? Well, what if I just get rid of the sun? It's just a black hole. Where will this blue object go? Into the black hole. So only things that would have fallen to the surface of that star or that sun get sucked into black holes. Things that are way out here where the planets are orbiting, well, they just keep on doing what they were doing. So black holes don't suck everything into them? That is true. They do not. Yeah, because it still has the mass. It still has the mass. And we're done with black holes?
Yeah.
Good enough? It's fun to talk about, eh?
Yeah.
You know, black holes really suck.
Right.
Thanks, Kaylee. Vacuum sucks. Totally. All right. So, which of the following diagrams most closely represents the gravitational forces that the Earth and the Moon exert on each other? So, I just want to point out, the mass of the Earth is about 80 times that of the Moon. So we have Earth and Moon. Now, is this like to scale?
Yes.
No.
Not to scale. Does that E look 80 times bigger than that M? No, not to scale. But, okay, so which of these is the best represents the gravitational forces that exist between the Moon and the Earth? So, in other words here, this is the force that the Moon is attracting on the Earth, and this is the force that the Earth attracts on the Moon. So, how many people said A?
Wait, what?
This, that's okay. This is the arrow here. This is the force that the Moon attracts, the force that the Moon applies to the Earth. And this is the force that the Earth applies to the Moon.
Can two gravities pull on, like, can a gravity pull on another gravity?
Well, gravity's not an object.
I guess
What is it?
two gravity.
Hold that thought. Okay, so how many people said B? That the force on the Moon is this much here, and few? Okay, how many people said C? Lone Jared, the lone wolf. D, anyone? E, anyone? F, anyone? G, I didn't do it because I didn't want to be wrong. Be brave, you guys. Be brave. The correct answer,
Oh, it's two.
Jared. Way to go, my friend. What did you get two, Anna? Why didn't you be brave and say, yeah, be brave? Oh, you did. I'm
So
sorry.
which one was it?
It is C. What did I say last year all the time? Equal!
Hey, Jared.
I wait a minute.
And for every action force, there is a equal and opposite reaction.
I was going by the gravity.
Equal. Right? Okay, so let's talk more about this then. Here's my Earth. Here's my Moon, right? Anna's so happy that she got it right that her sweater is lighting up. It's like the old days at the disco.
I'm gonna get it.
So why does the Moon orbit here? Because of gravity. How come the Earth doesn't orbit the Moon?
The gravity is stronger on it. Or the Earth's gravity is stronger than the Moon's.
Equal.
Earth has
Earth has
a bigger mass.
a bigger mass. Earth has an 80 times bigger mass, right? 80 times bigger mass. Okay, so let's just talk about scale here a little bit. Here's my Moon. Now, this is actually a scale model of the Earth. This is probably too big for the Moon. A golf ball would be better, size-wise. How close do you think the Moon orbits, like scale-wise here? Like, where would I? Tell me where to put it. How far away?
Whatever that is.
I think closer. Like right there.
Really close.
Halfway.
Oh.
Scale, yeah. Right here?
Oh. Well, it's on, it has an oval orbit on there, doesn't it?
Yeah, a little bit, but you know.
I think further.
How far, Josh?
Right there.
Right here.
I want to say like stupidly far away, but I don't think that's right.
How far, Jared?
Like way, like too far.
Like here?
Probably.
Maybe.
Mars.
It takes 3 to 4 months to get there.
3 days.
3 days.
I
Yeah.
think it's really close. So closer.
Closer.
Like we're ahead. I think
Stupidly far away.
All right. Well,
Compare like.
I just want to point out here, Manitoba. Anyone ever driven like right from like Ontario right to Saskatchewan? Oh, actually no. Let me rephrase that. How many people have driven this sort of like Calgary in a day? And you've probably driven from one end of Saskatchewan to the other, right? How long does it take?
About. No, more.
No.
Right. Okay, I can cover Saskatchewan with my pinky.
Damn.
Yeah, they're going a whole lot faster than 100 kilometers an hour. I'm going to stand where the Moon is relative to the Earth. Let me just sort of get this right here.
Way over there.
So,
Yeah.
Called it.
Good.
Dan, don't come back.
Yeah.
We lost
I called it.
Be brave, Jared. You're usually right. It's way over there.
it. Should be closer.
Equal and opposite.
Okay,
Go ahead.
the two people on there's another gravity can pull on another gravity. Yes.
Gravity can't pull on another gravity.
Or
Like,
when you enter
the Earth and the Moon have their own gravitational field, and they both exert that field on each other. I mean, that is literally the law of universal gravitation, right? Every two objects' masses will exert a gravitational pull on each other. That is equal. Why does the Moon orbit the Earth? The Earth is 80 times larger than the Moon. Okay? Would you like to watch a video about it?
Yes, please.
If you think back to like that first week when I ranted and raved about theories and laws and all that stuff, remember that? So gravity, people like to talk about, well, theory of gravity, but is it a theory? It's really a law, and it's an equation. It's F equals big G m1 m2 all over r squared, and no, you don't need to be able to use it yet. M1 and M2 stand for the two masses. G is the universal gravitational constant, 6.67 times 10 to the minus 31. And how do I still know that?
It's easier for us to learn it.
Divided by r squared, which is the distance between them, right? So you can use that. If you take the mass of the Earth, which you can look up, and the mass of you, right, and you know the radius of the Earth, you're going to get your weight force, which is going to be, like, you know, when I jump on the scale, and what do I weigh? About 800 newtons? You get about 800 newtons. Because that's how much you are attracted to the Earth, and that's how much the Earth is attracted to you. Okay. Do you have this sheet here, the one that says free fall explained? Find that one for me. The one that says free fall explained. It's a booklet, yeah. Nope. They land at the same time. Okay. Okay, read along with me, will you? Galileo showed, and I'll be highlighting. How will I be highlighting? Because I don't have it up there. So how will you know the important parts or the things that you will hear it in the tone of my voice? I will slow down and speak loud.
Like that?
Like that.
Yeah.
Galileo showed that falling objects accelerate equally, regardless of their masses. This is strictly true if air resistance is negligible. What does negligible mean? Negligible means so small that we can ignore it. Strictly true if air resistance is negligible. That is, if the objects are in free fall. It is approximately true when air resistance is very small compared with the mass of the falling object. For example, a 10-kilogram cannonball and a 1-kilogram stone dropped from an elevated position at the same time will fall together and strike the ground at practically the same time. The experiment said to be done by Galileo from the Leaning Tower of Pisa demolished the Aristotelian idea that an object that weighs 10 times as much as another should fall 10 times faster than the lighter object. Galileo's experiment and many others that showed the same result were convincing, but Galileo couldn't say why the accelerations were equal. The explanation is a straightforward application of Newton's second law and is a topic of the cartoon Backyard Physics, which I will look at in a few minutes here. So Galileo was first. He was the guy that did the experiment and said, okay, yeah, they land at the same time. He couldn't explain it. Newton was the one that came along. Actually, Newton was born the same year that Galileo died, and he was the one that sort of explained it. Recall that mass, which is a quantity of matter, and weight, the force due to gravity, are proportional. In other words, they are, like, if one goes up, the other one goes up as well, right? A 2-kilogram bag of nails weighs twice as much as a 1-kilogram bag of nails. So a 10-kilogram cannonball experiences 10 times as much gravitational force. Is that true? Things that are bigger, more massive, have more force on them? Yes. Right? Yes. So a 10-kilogram cannonball experiences 10 times as much gravitational force or weight as a 1-kilogram stone. The followers of Aristotle believed that the cannonball should accelerate at a rate 10 times that of the stone, because they considered only the cannonball's 10 times greater weight. However, Newton's second law tells us to consider the mass as well. A little thought will show you that 10 times as much force acting on 10 times as much mass produces the same acceleration as the smaller force acting on the smaller mass in symbolic notation. Now they've got it there. You can just sort of watch. I'm gonna write it out here. Here's Newton's law. F equals ma. And if I solve for acceleration, and you haven't seen a whole lot of this before, but if I want to isolate that a over there, I have to divide by m, right? You guys know that kind of stuff, right? And so those m's will cancel, and I'm left with a equals f over m, right? Well, if I've got a much bigger m, much bigger mass, then that means I have a correspondingly much bigger f. And that means that they both give us the same acceleration. And here on Earth, what is that number? 9.8. 9.8. Okay? That's just what it is. It just is. What actually determines that number? The mass of the Earth. Right? It's how big the mass of the Earth is. Is the mass of the Earth changing? How so, Taylor? You don't know?
If you fly something in space, then
There's less mass. So when we send the space shuttle up, right, and leave it on the moon, like the flag that they put on the moon back in the late 60s is still there. So is the mass of the Earth less? Okay, sure. But I would also argue that there's things that fall from space, right?
Yeah.
Probably more that actually fall from space than leave space, because one's occurring naturally and the other one takes us. It's, we are talking like there's the Earth, right? We are talking like a speck of dust, like Horton hears a who kind of thing on that globe, right? Insignificant, completely insignificant. Okay, so there you can see there on your sheet there where they got the F over the M, and it says where F stands for the force, the weight acting on the cannonball, and M stands for the corresponding large mass of the cannonball. The small f and m stand for the smaller weight and smaller mass of the stone. We see that the ratio of weight to mass is the same for these or any other objects. All freely falling objects undergo the same acceleration at the same place on Earth. In chapter 2, we introduced the symbol G for acceleration. Is gravity the same everywhere on Earth?
True question.
Ish. I mean, it's in textbooks, like in high school, it's 9.8, right? Is it minutely different at the top of Mount Everest?
Yeah.
Yes. Will you weigh less at the top of Mount Everest? Yes, except for the fact that you're wearing like 6 layers of clothes, right? But you are technically farther away from the center of the Earth. So. We can show the same results with numerical values. The weight of a 1 kilogram stone is 9.8 newtons at Earth's surface, and the weight of a 10 kilogram cannonball is 98 newtons at Earth's surface. The force acting on a falling object is the force due to gravity, the object's weight. Using Newton's second law, the acceleration of the stone is, and you can see it right there, 9.8 divided by 1, which is 9.8, or 98 divided by 10, which is also 9.8. In the famous coin and feather in a vacuum tube demonstration discussed in chapter 2, which I didn't talk to you guys about, the reason for the equal acceleration was not discussed. Now we know that both freely falling objects fall with the same acceleration because the net force on each object is only its weight, and the ratio of weight to mass is the same for both. So what is this famous coin and feather demonstration that is so famous but you don't know about? Well, what you do is you get a glass tube, and I actually have one back in my other room. It doesn't really work that well. And inside is a little coin and a little sort of feather, right? And when you flip it upside down like those rain sticks, the coin goes clunk chunk, and the feather goes, right? Which is kind of what Aristotle was thinking about. Then you hook it up to a pump and you suck all the air out of there, right? And then you turn it upside down, and what happens? Fall at the same time. How come?
No air.
No air resistance. Okay? Now, the one that I have doesn't work that particularly well because the vacuum's really hard to get a good seal and get all that air out of there. And then when you do that, then there's a fair bit of pressure on it too, right? So it's kind of a neat demonstration, but it doesn't really work that well, right? But if you were on the moon, like if I could magic school bus you to the moon, that'd be fun, eh? Oh, can you imagine the paperwork I'd have to fill out to take you guys to the moon?
Better be in your room.
Right?
Better be in your room.
Yeah. Oh. Yeah? That principal couldn't have been very smart if he didn't realize about that much school. Is that right?
Well, yeah, they only ever showed that one class.
Yeah, but that's just the one class in the school.
Well, they never had recess for other kids, just that.
You're not always.
And why weren't the other kids mad? How come we don't get to go to the moon and all those cool places? Because there's no way those kids could keep it secret for that long.
Because they wouldn't believe them.
I guess. We're not going again. And there was always that one kid that was always causing trouble. Who was that kid? I don't know. There was always one kid that was always getting lost or whatever, right?
Oh, yeah, it said like sucked into a body.
Oh. Okay, can I have 30 seconds and then I'll come see you? Okay, so if you were on the moon and dropped a hammer and a feather, here, let's ask Sammy if she knows. You know this answer, Sammy? If you were on the moon and dropped a hammer and a feather from the same elevation at the same time, would they strike the surface of the moon at the same instant? Okay, come get a clicker.
Yeah.
You don't want to do clickers?
Oh. Not today.
All right. Would they land at the same time? Now, if only there was video of this happening. Oh gosh, if only there was.
I bet there is.
No.
What?
David Scott was a NASA astronaut. He went to the moon. He took a feather. He took a hammer. He went out on the moon's surface, dropped them at the same time. Let's see what happens. How come they fall at a slower rate? Because the gravity on the moon is less. It's 1.6 meters per second squared. There's no way they can fake that.
Why is the flag on the moon wiggling?
Why is the flag on the moon black?
Okay, you guys, Art, be this weekend. Okay, flip the page over. Let's look at the cartoon. Now, do you remember that video where the professor wearing the acid wash jeans was doing the pulling with the girl, right? Remember that? Right?
Physics with an F.
Physics with an F, yeah, that guy, right? He's a textbook author, he's a noted science teacher, award-winning actually, and he also draws cartoons, so this is one of his. It's not a funny one. Yeah. So, there's two kids, they're looking at a lady, she's going to hang her washing out the window here, and she says, if I drop the bag of clothespins and the single pin at the same time, which will fall to the ground first? Okay, the one kid says, that's easy, the bag of clothespins is heavier, which means gravity pulls on it with more force. Is that true? That is true. Bigger mass, bigger force. FW equals mg. Bigger mass, bigger force. What's the same? I'll get to that. So, he says, so the bag of pins will accelerate more and hit the ground first. The other kid scratches his head and says, physics, physics, physics. And then says, not true. The bag of clothespins has more mass. Is that true?
Yeah.
Which has to say more inertia. Also true. It will be less responsive to gravity and lag behind the single pin. So the single pin will hit the ground first. Right? The lady drops the, where's my scroller here? The lady drops the stuff, and what do you know they land at? The same time. Just like the Jake Rampton and the Galileo, right? They land at the same time. How come? Because the bag has both a greater weight and a greater inertia. One offsets the other. Remember I wrote m over a, or m over, no, it's F equals. I wrote F over m is equal to a, and then I wrote big giant F over big giant m. The same acceleration. Let's talk about falling. There was this one here. You're going to have to listen to me last day. Sorry, guys. I'm keeping an eye on the clock. I'm going to try to time this just right. So far, I'm a little behind. Nope. Just got to sit back and enjoy the entertainment. I never did this in the morning class. That's one of my favorites. Remind me to do the book thing on the back. I got to get to that. Forgot to do that in the morning class. Okay. The feather of the coin fall with equal acceleration vacuum, but quite unequally in the presence of air. When air is let into the glass tube and is again inverted and held upright, the coin falls quickly while the feather flutters to the bottom. Air resistance diminishes, the net force is acting on the object. The net force decreases a tiny bit for the coin and a lot for the feather. The downward acceleration for the feather is very brief because the air resistance builds up quickly and counteracts its tiny weight. The feather does not have to fall very long or very fast for this to happen. When air resistance on the feather equals the weight of the feather, the net force is zero and no further acceleration occurs. Did you catch that? When the air resistance on the feather equals the weight of the feather, the net force is 0 and no acceleration occurs. So what does that mean? No acceleration occurs. That means that it's falling at a constant speed. Does it keep falling? You betcha it does. Okay? If I drop now these were, this morning, identical pieces of paper. In fact, they were identically folded. And I crumpled one up, as you can see, right? Do you believe me that this paper is the same as this? Or do I need to actually get a piece of paper?
I believe you.
You believe me? Okay. And if I drop them, they'll land at the same time, right?
Air resistance.
Jake Rampton. How come?
Air resistance.
Air resistance, exactly. Okay? So the force of air resistance equals the force of gravity, and so it no longer accelerates. It just keeps falling at a constant speed, which is really, really slow because it happened almost immediately. So this guy, go ahead, Anna.
What about if you dropped a water bottle?
How high?
I don't know, the same.
Like here?
Would be the same here.
An empty one or a full one?
I don't know, why not?
Do a full one.
Well, a full one would weigh a whole lot more, right? Like, is this going to have air resistance on it? Uh-huh. Is it going to matter? No. Now, if I were to take this to the top of the high rise, I always love that, high rise. It's like, what, 8 stories? You take it to the top of the high rise and drop it, will it have a force of air resistance on it eventually? Or will it accelerate all the way down?
Will that little paper be the same?
She said, will the paper, the couple on the other side one?
Oh. Well, these not the same. Is this what you're asking? Oh, okay.
Yeah.
Pretty cool.
Okay. So the surface areas matter. I need to do some more reading here because I kind of forgot where I left off. If we're concerned with direction, which is down, oh, I didn't say this. Acceleration terminates. The feather has reached its terminal speed. When I say terminal, what do I mean? I mean maximum. Terminal speed is maximum speed. We're concerned with direction, which is down. For falling object, we say the feather has reached its terminal velocity. Terminal velocity. It's falling as fast as it can. Now, why is this? Here's what happens. Okay? The object falls, it has a weight force on it, right?
Yeah.
And as it speeds up, when it starts off, there is a bit of wind resistance, right? A little bit of air resistance. Now, have you ever stuck your hand out the window driving down Main Street? And then done this, right? Lots of fun, right? If you put your hand out driving down Main Street, your hand kind of goes back, like you can feel it, right?
Yeah.
What if you put your hand out the window driving down the highway at 105 kilometers an hour? You might. Don't do it. Yeah. You might hurt, right? Yeah, and then this is fun, right? Why? Hands the same size. Why does it go back more when you're on the highway? Going faster. The faster you go, the greater the wind resistance. So as this thing speeds up and up and up, this wind resistance gets
Bigger.
bigger and bigger and bigger. And eventually these two are
Balance.
balanced. And when they are balanced, the net force is 0 and it hangs in midair.
And does no longer accelerate.
No longer accelerates. Which means it falls at
Terminal velocity.
terminal velocity. Terminal velocity. Now, in the case of the sheet of paper, when you drop it, when does it reach terminal velocity? Right now. Like immediately, right? It reaches terminal velocity right away. Why? It's really wide. It's not very massive. When I drop the water bottle, it doesn't reach terminal velocity right away. How come? It's heavy. Not a lot of, right? Now, if I were to drop this out of an airplane, it would accelerate to a point, and then the air resistance would build up, and eventually it would fall at a terminal velocity. When humans jump out of airplanes, they fall at a certain rate, right? How do they slow themselves down?
Parachute.
Parachutes. What does that do?
Bigger surface area.
Bigger surface area, which slows you down, which means your terminal velocity when you hit the ground is only like 15 kilometers an hour.
I don't where. In Mexico?
Okay? Air resist. I'm almost done yet. I'm going to skip over some of this stuff here because I'm getting more out. Find me where it says terminal velocity. Find that? I'm going to read this next paragraph and then quit. Air resistance does not have as much effect on the coin. At slow speeds, the force of air resistance is very small compared with the weight of the coin. Its acceleration is only slightly less than the acceleration of free fall, or g. The coin might have to fall for several seconds before its speed is great enough for air resistance to equal and cancel its weight. Its speed at this point, perhaps as much as 200 kilometers an hour, would no longer increase. The coin reaches its terminal speed. Terminal velocity. The terminal speed for a skydiver varies from about 150 to 200 kilometers an hour, depending on the weight and orientation of the body. So what do you mean by orientation? Yeah, like if you fall like this, you're wide, you're making yourself as big as possible, kind of like going out on thin ice, right? You're going to fall less and less. If you go like this, you're going to go really, really fast, right? So if you ever, find yourself in a situation where you're on a plane, there's two of you, there's only one parachute, the other guy jumps out, the parachute, and you have to catch up to them, what should you do? Yeah, you actually literally want to go faster than it to catch up to them. Then you got to wrestle them, get the parachute on. That's always, I would suggest don't. I would suggest not. Okay, I'm going to read just a little bit more. A heavier person will attain a greater terminal speed than a lighter person. The greater weight is more effective in plowing through the air. Body orientation also makes a difference. More air is encountered when the body is spread out and surface area is increased, like that of a flying squirrel in Figure 512. Terminal speed can be controlled by variations in body orientation. A heavy skydiver and a light skydiver can remain in close proximity to each other if the heavy person spreads out like a flying squirrel while the light person falls head or feet first. A parachute greatly increases air resistance and cuts the terminal speed down to 15 to 25 kilometers an hour, slow enough for a safe landing. And I'm going to ignore the rest because it's really... Pardon me?
That's when you go down a slide, and all the big people are moving fast, and I never go.
Yeah.
Like the big dad bod, the local dad.
I remember I used to work daycare in the city in the summer, and I would take the kids, and we would go like, we'd put the kid on my chest and we'd slide down together. Kids just loved it because I could go a lot faster. Okay, flip the page over here. See the guy with the book? It says, if you drop a sheet of paper and a book side by side, the book will fall faster because of its greater weight relative to their resistance. So I'm going to demonstrate. Now, I usually have a textbook in here. Who's got a textbook that's kind of the same? Is there a book there? Who's got a textbook? Anyone? That'll work. That'll work.
English dictionary.
No, I used to be the same size. So pretty close. Anyone else got another book that's slightly bigger? No? Okay, I'll do this. Okay, so if I drop these side by side, they're roughly the same size, of course. Which one's going to land first? No big surprise. How come? It's the air resistance is the same, but this is heavier, right? So it doesn't reach its terminal velocity just yet, okay? Because the weight for the air resistance is the same, but the weight force is considerably more. It hasn't reached terminal velocity. Now, what if I do this? Drop it with the book underneath.
The paper's still going to fly off because it's not the same size.
I think the paper's gonna stay.
I think it will stay.
Think it will stay with it?
It will stay with it for a longer period of time, but it will still fly off.
I think it'll eventually.
It'll take it for a little bit.
Okay. Ready?
If you drop it,
Stayed all the way.
what if you drop it from a
Ah,
high?
if you dropped it from a higher, maybe, yeah. Usually, I know I have a book in my room that's the same size. That's the book I usually use. Teague was saying that because it's sort of peeking out over the edge, that it's gonna, right? I was surprised actually. I thought it would separate a little bit.
When the Titanic, or when big, huge ships go down, so like, you know how the mast goes under and everything on top where the smaller mast gets sucked in?
That's an action.
Does it? Not at all.
Mythbusters proved it.
Really?
Yeah.
Like shit, so they don't suck anything down.
What if you hold it like this? And the book.
Will the light paper hold the book up and let it go like this? Oh, that'd be so cool. If only I had Jedi powers to do that. Yeah.
What if you did that?
Okay, so now
After you, a really big piece of paper.
you want to know this, right? Is this what you want?
Put it like this, like.
Oh.
Will it come up?
All right.
Yeah.
Yeah. So there's enough air resistance on the side.
Yeah, so it's talking about the first.
Okay. Is that enough? Can I quit early? 4 minutes?
Yeah.
That's probably good enough. Yes, Josh. Work.